All righty. Looks like we're finally going live here. So our goal is to talk about energy problems. And in case you're just coming in, remember, I'll go over the quiz later in office hours, or we've got office hours tomorrow or something like that. So at some point, we have to get into the next topic. And let me shut this door just so I don't have to listen to my kids real quick. All right, so let's not think about the quiz. We got to suspend thinking about the quiz for a bit, get to the new topics. That way we don't get behind. And so I just want to do a quick rehash of where we left off last time. I don't know if you remember this, but we talked about some equations like gravitational potential energy was mgh, or sometimes we called it mgy. We talked about spring potential energy, and that was 1/2 kx squared, where x is the amount of stretch or compression. We talked about kinetic energy, which was 1/2 mv squared. All right. And then we noticed there was this thing sometimes appearing in the equations. I called it work from non-conservative forces or external forces. All right. And this could be variable on the situation. It might be related to friction, for example. Friction is a non-conservative force, or maybe a zombie pulling on a string or something. That could be an external force. All right.
Professor Joseph,
Yes. Go for it.
I'm sorry to interrupt,
Yeah, go for it.
but since I started the exam, Canvas kicked me out and it's not functioning in neither of my devices.
Yeah, the quiz is over.
Yeah,
The
yeah,
qu-
yeah, yeah,
yeah.
but I'm not able to log into Canvas anymore. Like
Oh,
I have to ask a friend to send me this link
okay.
because I'm
Well,
not able to.
okay.
Or can I talk to you like
Yeah,
after
this is not
class?
a, yeah, let's talk after. All right. Let's focus on the next thing. All right. So,
All right.
now there was
Thank you.
Canvas problems earlier in the day, but there was a notification sent out that it was back up and running in the hour before your quiz. And so, to my knowledge, it was all good. We could worry about that later. All right. So,
Sounds
yeah,
good. Can I
yeah.
email you the
You can email
screenshot?
me whatever you want. I want to get back to the content. So this is not the time to be, yeah, I know you're upset about it and that you want to talk about it, but I need to get on with the lecture just because. All right. So email me whatever you want. All right. And we'll talk about it in office hours, just not in the middle of lecture when everybody's here waiting. So, all right. So we have, um, all right. So where was I? There's these types of energy, there's this work term. And so, in general, what do we want to do? We want to look at potential energy of different types plus kinetic energy of different types plus any external work done or any work associated with non-conservative forces should equal the final potential energy plus the final kinetic energy. All right. And so maybe I'll put some initials and finals on here. All right. So in this case, we're talking about, you can remember we talked a little bit about this like it was a bank account, right? And so we were saying um, you could have some money in your savings account and you could have some money in your checking account. These would be like paychecks coming in or bills that you're paying going out, something leaving the system. And then there would be some final money in your bank account as well. And so the idea here is if there's no money coming in or out, we expect the initials should equal the final. It may change between savings and checking, but yeah, we'd have the same amount of money initially and finally, or the same amount of energy initial and final. That, when this term is equal to 0, is called conservation of energy. All right. And so in practice, what do we do? We're going to be doing basically a before and after picture, analyzing the problem and figuring out what types of energy do we have at the beginning, at the end, and if possible, is there any of this external or non-conservative work being done? write an equation, solve for something, evaluate the answer. So that's kind of our goal today. All right. And so, yeah, let's start with a screen share here. Let's get to this one. Yeah, let's do that one. All right. Oh, and that's a little far ahead. Let's scoot back here. So I think we last time left off somewhere on this page, right? Yeah, I think we kind of alluded to maybe looking at 8.10. So maybe we'll start there here in this case. So we're going to start with 8.10. So I'm going to go ahead and get this drawn up, and you could go ahead and get it drawn up as well. Okay. Draw this one here. All right, let me draw this one here. Okay, got it. All right, so this is 8.10. All right. So we have a block that's sitting up here, and we're told it's some distance h up above here. All right. And then we know that right here, we're told the spring compresses some distance. I think it said x. Did it say x? Whoops, I lost it. Where did it go? Oh, it doesn't tell us how much it gets compressed. All right, so that's fine. So maybe we'll give it a name. Now, we're going to see that even though this is a vertical compression, many problems actually label this as X, but we could actually label it as Y as well. So it's going to, and I think that is not listed in the problem. Just double checking. In part B, it says it does compress. So it does say X. So in part B, it tells us this is going to compress some distance X. All right. So I thought it said that somewhere. And what is our goal in part B? We're supposed to figure out the spring constant. So our goal is to find the spring constant. And let me just draw the block here. Moving, I forgot to draw that. So right, the block is going to be moving down here. It's got some speed. And when it gets to the bottom of when it gets to this max compression position, how fast is it moving? When it bottoms out.
Are you saying like at the very bottom? Isn't it?
Yeah,
Velocity,
at the max. Yeah, go ahead. What was that?
Velocity is 0, right?
Yeah, exactly. So when it bottoms out, we know velocity is 0. In this problem, what was the initial velocity over here? Was it released from rest? Yeah, it was. So we know its velocity was 0 here as well. So maybe I'll keep track of this by calling this V1, V2, and V3 instead of initial and final, just because I happen to draw 3 pictures here. It turns out this middle picture is not even necessary at all, but that's okay. All right. So now in this problem, we're going to do an energy problem. And so one of the first things we have to do when we do an energy problem is what? Do you remember? It's okay if you don't.
0. The base equals 0.
Where is 0? Yeah. So there's 2 obvious choices for 0 in this case. You could say at the lowest point. However, this problem is one that very oftentimes will say this height is 0. And so this is the one exception to making the lowest point 0. It's usually very common to set the initial height of the spring as 0. Well, it's yeah, let's do it that way so you could see what would happen. So in that case, let's start out. What types of energy do we have initial? Is there initially kinetic energy?
No.
No. How about U initial due to gravity? If I set this as the 0, so this is my reference level all the way across, what's the initial gravitational energy according to this reference level?
MGH.
MGH, and that's convenient. We don't get an MGH plus X. All right, so then in the next one, how much spring energy are we using initially? Is the spring initially compressed or stretched, or is it not being used?
Not used.
So we get a 0 for that. Now, in the end, let's use all the way over here to stage 3. So this is the final state, okay? And this is the initial. If we go all the way to the final state, what is K final?
0.
0, absolutely. What's the gravitational energy final?
MGH plus X. Is that?
mg delta
Oh,
x.
yeah, sorry, my sound cut out for a second there. Yeah, when my child came in and touched the cables and it locked up. Go figure. All right. Can you hear me now or not?
Yes.
All right, sorry about that. Okay. So yeah, what is the gravitational energy here? Mg times what's the vertical position
H plus X.
for this final state? It's not H plus X.
Oh, is it just X?
Nope. But close.
Negative X?
Negative X, because I'm down from 0 by X. And so this is the part that's a little bit weird. So I just want to pause and make sure we got that. So if this is 0, that makes this height positive H, and this height would be negative X. So that's the issue with picking not the lowest point in the problem as your reference level. And now that we see that, hopefully you know how to handle that. Any questions on why I did negative X? Sounds like you're good. Okay. Now the spring final is 1/2 kx squared. And notice we don't have to worry about the minus sign here. The energy is a positive value in this case, so the squared takes care of that for us. We don't have to think. All right. Now, in this particular case, there's no work done by friction. We're ignoring air resistance, things like that. There is a normal force between the platform and the block. However, that's an internal force to the mass spring system, right? So that's not doing external work. It would do, right? The block is going to work downwards on the platform, whereas the platform is going to do work upwards on the block. And so it's like, whatever. That network on the block spring system is 0. So in this particular case, the external work or non-conservative work should equal 0. Remember this. You might be saying, well, wait, doesn't the spring do work? Absolutely. But we've already accounted for it in the spring energy equation. Doesn't the gravitational force do work? Absolutely. But we've accounted for it. If you remember, work equals negative delta U. So if you talk about the gravitational energy, we've already accounted for the work done by it. If you talk about the spring energy, we've already taken care of the work done by it. At this point, we could say E initial plus, oops, let me get just a little bit. E initial plus work, external and non-conservative, equals E final. All right. So now in this case, this is 0. E initial is all of the initials. E final is all of the finals. You add them up and we solve for the letter K. So now I'm going to bring that up on just a second, but any questions about that? Let's take a look at it here. Where was it? Oh my gosh, one more. There we go. And so this is just showing you that issue. I think there's the answer, and there's a bunch of words on it, so you could read this and you could read all this kind of stuff here. So there's a lot of extra notes in there if you want them. Okay. All right. That's pretty good. Let's go back to another problem now. So our goal today is just to do as many problems as we can. And so I go through all the rest of that in there, but we did the hardest part of that. It was setting up the equation. After that, it's just algebra, not physics. Just solve for some equation or some symbol in the equation, excuse me. Okay, 8.11 is a really good problem. And so I'm going to leave this one for you guys to do at home because I know I put a lot of extra diagrams in that last time I taught the class. So 8.11, I'm going to let you look at. But boy, there's a lot of good nuggets in this problem. So this is worth looking at. That said, I want to work at 8.11 and a half. So let's take a second to look at that while I get it sketched out. You go ahead and kind of read it and kind of get your brain wrapped around it. 8.11 and a half. I'm just getting it sketched out. Let's see, D is the total distance. Okay. Kind of sloppy. I'm just going to write down all the givens. We know M, X. Looks like G is a given. We know this mu static, mu kinetic are given. Looks like D is given and theta is given and V. D, theta, V. Just reading through it. X and M, D and theta, mu static, mu kinetic, V and G. Got it. Find the spring constant. Now, as cheesy as this sounds, I'm going to go ahead and write WTF. Remember, what variable was the spring constant again? What letter? K. Yeah. So the idea is here, these problems, the equations start to get pretty long. So making a note to yourself of what you're looking for is useful sometimes. All right. Okay. And so here I'm just listing out the stuff that are given. And the idea is it's a puzzle. Now we want to get this letter and have only those letters in the answer. Okay. So in this case, will there be spring energy? Yes. Will there be gravitational? Is this block going up and down? Yeah. Oh, go ahead.
Sorry, I was going to say no, but yeah, it is because the incline. So
The incline, yeah. So it's not going horizontally, it's going up some. Okay. There's going to be kinetic energy because we see initially it's at rest, but at the end, is there going to be work done by an external or non-conservative force?
By friction?
Mm-hmm. Friction, will that tend to do positive or negative work? What do you think?
Negative.
In this case, yeah, the friction, if this block is sliding that way, friction's going to be that way. It'll do negative work. So we expect some negative work associated with friction somehow. So let's go ahead and start writing. I think we've got all the main pieces. And so this is a really good problem. So let's start simple. What's the initial kinetic energy?
None.
None.
Zero.
Why? What's the key
It's
word?
starting. It's released from rest.
Released from rest. Okay. Oh, what's something that we do in every problem right at the beginning?
Reference level.
Reference level. So this time, let's set the bottom as the reference level. Now, all right, that's good. So we've got that reference level. So if that's the case, what's the initial gravitational energy?
0.
Cool. And so that's the advantage of picking your reference level. You could pick at least one of the gravitational energies to be 0. So usually you pick the lowest one, so you don't have to think about negative x. Ugh. All right. What about spring energy? Initial.
One half kx squared.
Exactly. We're told the distance x, so let's do it. One half kx squared. All right. Let's do the final energies. Kinetic final, 1 half mv squared. I'm going to skip over here and do the spring final. What's the final spring energy? Once this block comes, it's going to separate from the spring and slide up. Once it separates from the spring,
0.
0. So now all that's left is U due to gravity final. So it's going to be M, G. What's the final height?
H.
Okay, H. That's good. What is H? H is not one of our givens. So we have to rewrite H in terms of the givens.
D sine theta.
Let's check. I forget. Okay, if we know, let me just draw a quick triangle here. Sorry, let's do a side problem. If this side's H and this side's D and this is theta, yep, height is going to equal D sine theta because it's opposite. So I'm going to write D sine theta. And that's kind of the trick in this problem. Without that, we're toast. Okay, so far so good. Any questions about how I got that height? That's the final height. Okay, and now for the sake of space on the board, I need to erase that. All right, so now we already discussed there's work. What's the work done by the normal force in this problem?
Zero.
0. Why?
It's perpendicular.
Perpendicular to displacement, right? Okay, so we don't have to worry about that. We've already accounted for the work done by gravity and the work done by the spring. All we got left is friction. So let's do that. So let me lower this down just a little bit. If I want to get the work done by friction, we have to go back to chapter 7. So generally speaking, this technique of chapter 8 is so much easier than chapter 7. You're never going to use chapter 7 except when you have to get the work done by a non-conservative force. And obviously that definition helps us understand this chapter. But in this case, we actually need the chapter 7 technique to get the work done by friction. Well, does anybody remember the equation for work done by a force in general?
Normal
Force times distance cosine theta.
Cosine of some angle. Yeah. And so, Alonzo, what were you going to say about the normal force? Go ahead. Bring that in there.
That the normal force times the one of the coefficients.
Yeah, exactly. So you're kind of addressing this piece right here. So he's saying that's mu in this case. Should I use mu kinetic or mu static?
Kinetic.
Kinetic, because the block is sliding up the ramp. Nice. All right. And then, shoot, how do I get the angle? Do you remember?
They're going in opposite directions, right? So it's 180.
Yeah, so I draw a picture. I know this is the displacement. I know the frictional force is this way. So remember, the angle is not necessarily theta, and that's a common mistake. The angle in this case is 180. That said, what's the normal force in this problem? How can I figure that out?
Should be equal to gravity,
Hmm.
right? Oh, wait, no.
What's the general technique I could do to figure out a normal force?
FBD.
FPD?
FBD. Okay. Now, you could say, what about the spring force? You bet. There may or may not be a spring force during part of this problem. Agreed? However, does the spring force affect the normal force and its equation? This thing is accelerating up there, right? At least while the spring is being applied, right? It's accelerating up the ramp. But that doesn't change the components perpendicular. So these things relate, sure, to the acceleration. However, the normal force is going to be mg cos, right? Mg cos. So now I have all the pieces. I know all the different types of energy. I know the work done by friction. I know cosine of 180 is negative, so I get a negative number for the work done by friction, like we expect, because friction is slowing me down. Negative work slows you down. I know that this is true whether it's got the spring on it or not, although the acceleration direction changes when the spring force is gone. We're ready to plug in all the pieces. So before we go on, let's just try and get it all on the screen here at once. If I could raise this up just a smidge and see if there's any questions about any of that junk. That's a lot of junk.
So are you saying that mg cosine is equal to the friction?
No, I'm saying mg cosine theta is equal to the normal force, which relates to the friction. Close, similar.
So what's that box on the left then? I'm sorry.
Oh, that's plugging in for the normal force.
Oh, okay. Gotcha.
Thank you. That was poorly done. I agree. So the normal force is this. Do you agree with that? Is that better?
Yeah, that makes sense.
All right. Sorry about that. My bad. Other questions? All right. Let's go look at the solution and see what's up. All right. See if there's anything else in there that I forgot. Excuse me. So there's 8.11. You can see I put a lot of work into that solution. That's why I'm saving that for you guys at home when I'm not around. All right. So here is kind of this picture. There's the equation that we just found, basically, right? We said 1/2 kx squared was the initial. Then there's work done by friction. And then there's this. And then here's the FBDs, right? And so notice that it's this equation, the work done by friction, is going to be valid with either of these FBDs. Okay. So, and after that, it's just solve for the letter K, get a big ugly mess. Who cares? It works. I'm going to pause. Any questions on that? Okay. Okay. And if I go too quickly, let me know. All right. This is a pretty cool one, actually. It's showing all the different types of energy as a function of time. Those of you that somebody did this lab where there was a bouncing spring, but maybe I'll just kind of show you the solution really quickly. So this shows you what the energy plots look like for a mass on a spring. All right. And you can see that there's a mix of gravitational, spring energy, kinetic, and it's all over the place. So you could see all the equations and how they work out, but notice that the total energy is actually just some number, right? So this works out. All right, let's go back to here and see what I wanted to do next. All right. Okay, now we're going to start getting into more and more just kind of tricks to save you time. Let me ask you something. We're looking at 813 now. What's the first thing we usually do, or one of the first things we do in all of these problems?
Reference level.
Set that reference level. If I set this as the reference level right at the center mass, what's the gravitational energy in this problem?
0.
0 for both stages. So, aha, if you have a level ground problem, you can ignore gravitational energy. Why is that true? Because if you recall, delta U is the thing that matters physically. If the potential energy doesn't change, who cares? There's no physically meaningful observation that can be made to analyze that potential energy if it doesn't change. All right, so that's one thing. What about, there's no spring energy. So notice this one would look like kinetic energy, initial, plus we have some work done because there's friction. I suspect you agree it would look like this, work done by friction. What's the final energy for this problem?
Is it just all 0?
Yeah, it's all 0. And so sometimes we get the initial energy, you zero out your bank account. Unfortunately, we all know what that's like when you zero out your bank account. You run out of money or run out of energy, right? Okay. Disturbingly enough, just like in bank accounts, in physics, we can get negative energies too. All right. Let's leave that out for now and try not to think about it. All right. So in this one, it's very similar to the last problem, except there's a force applied. Now, the work done by the force plus the work done by the friction plus the initial kinetic energy. Again, I don't have springs because it's a level ground problem. I don't need to worry about gravitational. And because it's at rest at the end, you get a very similar type of problem. So we could see you could have multiple forces. This is an external force. So that's external. And this one right here, the friction, is the non-conservative. All right. So we can't account for that as well. All right. So I'll let you guys look at that one later. Ooh. So in this case, now, all right, I'll pause for a second. I hope I'm not going too quickly here. Any questions about those last two questions? The main thing was, if it's a level ground problem, you could ignore gravitational energy. All right. Let's do this one now. All right. So let me get back. Whoops. Come on. All right. So look at this 8.16 while I get the board ready. What types of energy are going to be involved in here? Do we have kinetic energy, at least in either the initial or final? Is kinetic involved?
Yes.
Yes. What about gravitational?
Yes.
Yes, the ball is changing height. No spring. Is there going to be work done by the tension?
Yes.
How much work? That's a clue.
Wait.
Yes, that's the right answer. Wait. Yes. Check it out. Here's a ball on a string. Whoops, I just dropped a marker somewhere. This is hard, so give me a second here. Sorry, it's not perfect. What do you notice about the tension relative to this path?
It's
It's
fixed.
closed. It's a closed path.
It's perpendicular. Look at that. The tension is always perpendicular to the path, is it not?
Yeah, so it remains the same.
So then it does no work. Remember that work equals tension times, you could call it S times cosine of, in this case, 90 degrees. It's always perpendicular. Well, that goes to 0. So remember, in circular motion, when things are swinging, the force towards the center does something. It produces the centripetal acceleration that causes this thing to go in a circle, but that changes the direction of velocity. It doesn't change the speed. So that means it does no work. It obviously matters. If it wasn't there, it wouldn't go in a circle, but it doesn't do work in the mathematical sense because it's perpendicular to displacement. It won't change the speed. Gravity is what changes the speed, right? Swings down and speeds up. All right. Oh, whoops, there's a chat there. Let me get that.
That was just me
Oh.
realizing.
Oh, sorry, I'm slow. Okay. All right. So, all right. So now in this case, I don't know if you, well, let's see. I think I hung this is the spot I hung the pendulum right here about. So I'm going to just kind of move this now. Get that out of the way. All right. So the idea here is now, just like the block on a ramp, the real issue here is not writing down the energy equation. It's doing geometry to figure out a correct gravitational potential energy. That's the crux of this problem, geometry. So in case you haven't seen this before, I'm just going to kind of go through it. I know that this point right here, all the way down to here, that's a radius, right? But so is this. This is a radius. And in this problem, let's say this is the angle. The height that we care about is going from right here to right there. That is the height that I want. And now this is kind of a confusing picture, so let me label this off to the side. I think in the problem I used L instead of radius, but who cares? We'll fix that later. We'll just set R equal to L. I'm going to get rid of this line here just so I can see better. That is the radius right there. So height, we have to actually figure that out in terms of the givens. The givens in this problem were L and theta, or radius and theta. So what's this side of the triangle?
R sine
Yep.
theta.
So what's this side then?
R cosine theta.
Our cosine theta, right? Okay, so in this case, how could we relate h to the radius and the angle? What's your gut tell you? Where'd that marker lid go? Go for it.
That line of y equals 0, the energy change.
You're maybe thinking more complex than I was. I'm
R
just saying,
co-
yeah, go for it.
R cosine theta plus H.
R cosine theta plus H is equal to R. If you rearrange that, you're going to find that H equals R times 1 minus cosine theta. So that's what I was looking for. Obviously, H does relate to the gravitational energy as well, like you said. So, oh, there's that marker lid. I got to grab this. Hold on. Crawling around. All right. So that's what I want. So basically, once we know that, the rest of the problem goes pretty easy. Let me share the screen. Remind you of this problem. Okay, so the idea is we were given this angle and this L. We just did a lot of work to describe the height of that. So if I go to the solutions now, where is that one? Right here. This is all sketched out for you. I hope this makes sense. I kind of did that another way, and I showed you the steps. All right, so in this case, the initial energy is all gravitational. The final energy is all kinetic. The H is the hard part. We use some stuff, blah, blah, blah. The tension does no work. We're good to go. Ooh, look at part B. If we do an FBD at the bottom, I'm going to talk about this one. Imagine we do an FBD at the bottom of the swing. The ball is not at rest at the bottom of the swing. It's moving sideways, right? So notice there's tension up. There's mg down. So is tension equal to mg? What do you think?
Tension should be a little bit higher.
Yeah. Is this thing accelerating?
Centripetally, at least.
Yes. And so the issue is T has to be bigger than mg because AC is present. Nice. All right. So now we get T equal T minus mg equals MAC, which this is V squared over R. So aha, that's where the velocity comes in. And if we go into there, let's go take a look at it. You can spend some time on this later and work out the details. But so basically, radius in this case is L. You get this unusual equation. Now think about it. What's the largest possible value, the smallest possible value we'd get for cosine in this problem?
0.
0. It wouldn't be negative. It'd be 0. So if this is 0, what do you get for cosine of 0 degrees?
1.
1. And then what do we get for the tension?
It equals mg.
Yeah, and so that makes sense. If theta is 0, the ball's just hanging there, not swinging, right? So that makes sense. This is cool. It makes sense even in that weird extreme limit. Whereas if you go to some higher angle, like say 60 degrees, cosine of 60 is a half. So this would be 3. You get twice the weight. So notice the swinging cable has more tension at the bottom than a ball just hanging there. This is cool. This makes sense. It seems reasonable. That's what we mean by do a reality check in a physics problem. I don't know if it's true or not, but I told the last class, so I'm going to tell you too. There's an old story, whether it's true, I don't know, but it's interesting, about a bungee jump company that used to have people jump straight up and down, they jump off. And then one time they decided to let people swing in addition to jump off. And of course, when they swing, you need more force. So the cable has to stretch farther and you kill a bunch of people. So I don't know if that's true or not, but yeah, this is like 20 years ago. So watch out for your bungee jump physics, okay? It's important to remember this crucial fact. It could literally kill you by neglecting this. The fact that a swinging object is going to carry more tension than an at-rest one. So it has major safety implications for engineering. All right, let's leave it at that. You could tell me if that's an urban legend or not later and say whatever. Okay. All right. There's that one. Where are we at now? Okay. And there's a variation on that in the next problem. Let's see, where was it? 8:16. I'm going to give you guys a break here in a couple of minutes, but just let me get through, I think, 2 more things. So that's a variation. I'm going to let you guys attack that one. It's very similar. So, this one. This is an important one. It's kind of the last of the big tricks, this problem. All right. So let's get this trick and then we can talk about a break. A Fletcher's trolley system, whatever, that's that thing. Okay, got it. We got a mass M and a mass 2M. What's the first thing we usually do in these problems, or one of the first things?
Reference level.
Where do you want to set the reference level in this problem?
At the table, like at the surface of the table.
Okay. But what do we know this distance here?
You should do from the 1M, the mass.
So what are we told, right? We're going to say, okay. Did I not specify this? Oh, it says how high above the ground. Oh, so we're looking for that. I got you. So we're looking for this height. All right, now I could make you stew over this for a long time. The problem is we don't know this height in the problem. We don't know that height in the problem. So it starts to get confusing and you might worry you can't solve it. I'm going to show you the trick so I don't waste your time, all right? Whoops, let me get rid of these annotations first. There's a cool trick you can do, and this is it. Set 2 reference levels. What? Firewood? You could actually do 2 separate reference levels, one for object 2 and a totally different one for object 1. And this is legal mathematically. Okay, that is the trick I would do. Because this is on a level surface, the upper block, we don't have to worry about gravitational potential energy at all for the upper block. So set its reference level to 0. Now, the other one does move up and down, so we do worry about it. Now, if you're worried about this in general being legal, I'm just going to show you something. Okay, let's think about this here. It's about right. Sorry, just checking. Okay, so this is supposed to be that same problem. And let's say we didn't know these distances, but we tried to label them. Like, let's say we set this as y equals 0, right? We know that this is y equals h, and this would be something like y equals h plus some unknown distance d, where d is this amount that it's hanging below the table, okay? So we could, in theory, do that. Let me get that a little closer. Now, if we do the energy equation, just hang with me for a second. U, due to gravity, for number 2, initial, would equal m2 times g times h plus d. Now, U, gravity for 2 final would also equal m2 g h plus d. Now think about it. This one appears on the left side of the equation, right? We've got U2 gravity initial plus a bunch of other stuff equals U2 gravity final plus a bunch of other stuff. Well, the M2GD on this side of the equation will always cancel out the M2GD on that side. And in fact, you could say, well, does this only work because it's level? No. What if this block went up or down? The H's might change, but you'd still have the D, the offset value. And so it is totally legal mathematically to use two different reference levels, because if you shift them, you're shifting the reference level the same way on the left and right, and the difference in potential energy is all that matters physically. And so the difference will be the same whether you set this to 0 or whether you set this to 0 here or whatever. I'm going to pause. Does that make sense? I'm trying to explain why it's legal to set two different reference levels mathematically. Now, I'll just say one last thing on this since I'm babbling. There's another way many physicists write this equation, right? I don't know if you remember, we said E initial plus work equals E final. That's how we've been writing it. To me, this makes sense. There's always an initial, some debits or credits, and then a final. However, you could also write this as work equals change in energy, which you could say that's change in kinetic energy plus change in potential energy. And the idea here is, well, only changes in only changes in potential energy have physical meaning. And so that's why some teachers love to write the equation this way. And there's some problems I do it. However, for me, it makes sense to do it initial and final. And then I just say, okay, the initials are with the first picture, the finals are with the second picture, and the work is anything that's external or non-conservative. So let's get back in there and take a look at it. Now, obviously, you need to kind of go through this problem, but let's take a look at this one. Okay, there's initials for kinetic and initials for gravitational. We don't have spring. There's work, then there's finals and finals. Now, I assigned separate reference levels. Any offset will always drop out. Tension, that's an internal force. That's why it does no work. Normal force from the table is perpendicular to displacement. That's why it does no work. Now, the forces from the pulley, they're not actually displacing the string, so they're not doing work. If you think about it, as the pulley twists, the string is remaining at rest relative to the pulley, and so you actually have static friction acting between the pulley and the string. That's tricky. We can discuss it later if you care. For now, just know that the pulley, we don't have to worry about that doing work. Okay, the work done by friction. Well, in this case, 2 mg is the normal force. Mu, and then where does the h come from? If this one goes down distance h, this one moves over distance h because they're tied together by a string. And so that's how the h gets involved. And again, if you want, you could say, well, there's an n here, and there's a 2 mg here. There's a tension this way, and there's a friction this way. I hope you're seeing why I pounded those FBDs into you. We just use them all the time. All right. And so they just show up at the weirdest spots. So it really has to be something you have down, because it could be in any problem at any time for the rest of your physics classes. All right. Ooh, this is a neat one. Both blocks have the same final speed. That gives rise to this. What I did is, because they have the same speed, these two terms have the same V. I factored out the V, and so I get mass total. If they're both being pulled by the right? If they're connected by a string, we expect them to move at the same speed. And then this one we kind of talked about already. And then once you're there, the rest is easy. Just algebra. I'm going to pause. Any questions on that? All right. You get some weird result. Great. All right. I'm going to go back to this one now. Evidently, there's a part B here. Determine an upper limit on the coefficient of static friction. How would you do that? What type of problem is that?
Does that have to do with calculus? Like taking no.
Nope. That's a good guess. What's another technique we could try?
FBD.
FBDs get the coefficient of static friction. The idea is, okay, so this is subtle, right? It looks like it's some weird calculus thing. It totally looks like that, but it's not. If we go into here, oh, look, I even say it's pretty tricky. Okay. The wording indicates the problem makes no sense if static friction gets too large. Think about it. If static friction gets too large, the blocks don't slide. That would be a physically impossible scenario. So you should do a force problem, set A, set it on the verge of slipping. That's a fancy way of saying it's on the verge of slipping. And that happens when mu static is greater than or equal to 0.5. So your coefficient of static friction has to be less than 0.5 or it's not going to slip. All right. So that was that one. Now it's almost time for a break. Let me do a couple of things. 8.19. Let's just look at it. The incline is frictionless, so we don't have friction. We're going to release this thing from rest. We got 2 blocks. Well, I'm not going to waste your time. I'm going to let's go right to it here. This is how I would attack that one, right? You have 2 different blocks, use 2 different reference levels. Now, here I've got to warn you, I was a little bit lazy, but it's still mathematically legal. Technically, you should always go from the center to the center, but I hope you agree going from the bottom to the bottom on a ramp, that's legal. If it was a curved surface, that's not a legal move. Again, here I should have gone from center to center, but that's the same as going from the bottom to the bottom when it's going straight. So if you have straight line motion, not curved motion, it's okay to use the bottom of the blocks as your reference, or the middle, or the top. All right. Now, in this case, I wrote out this problem and I wrote in this frictional force, and then I'm like, wait a minute. Oh, crap. I did all that work for nothing. Mu kinetic, I just set it equal to 0, and then I got the right answer. So at first I thought there was friction, and there wasn't. All right. I'm going to give you a second to digest that and see if this makes sense. Take a second to look at the energy equation and read the problem on the page in front of you and see if you understand why terms are there or not there, etc.
Before I do that, so again,
Yeah.
we can use 2. If we have 2 blocks, that's when we use 2 references, right?
Right. And if you had 16 blocks, you could use
16.
16 reference levels. Yep.
Gotcha. Okay.
Yep. Now, a lot of times if you're, I don't know, you could also use just one, right? If you were going to write a computer code, you probably would only be able to use just one. But if you're writing a computer code, you could very quickly figure out the distances between all the blocks and get those offsets very quickly. So that's fine too. You're welcome to use only one. Define that offset. In this case, to be clear, let me explain what I mean by an offset. So this is the 0 value for this one. Notice this one is offset from that by some small amount. You could give this a name D and do the problem, and then you wouldn't need this second coordinate system, but it's a lot faster to use a second coordinate system. Was that good on your question? Just making sure.
Yeah, it's all good. Thank you.
Right on. All right. Okay, so let me go back to the book. You can do 820 yourself. Here's some summary comments. So let's maybe look for just a second at this. Let me get some Zoom crap out of the way. Give me just a second. Okay, so here it all is. So this is the summary. Okay. Always, always, always think before just blindly using it. Is it okay to use work or do I not need to use work? Just double check. Just think. Are there any possible external sources? This is a common thing students forget. Okay. Basically, is there friction or not? It's not always true, but that's kind of, you'll see in a lot of problems. If there's friction, don't ignore that term. Remember this, forces pointing towards the center do no work. They change the direction of velocity, but not the speed. Got it. Forces perpendicular to displacement do no work. We've used that over and over again. For a two-block system, each gets its own reference level. Internal forces, like we saw the tension from a string on certain problems. Great. On inclines, we use this H equals L sine theta. I don't know if you remember that. That was something we saw. If you're on a ramp, the height is usually L sine theta. This is a weird one. Let's talk about this in depth. If a spring is changing length, force is not constant, right? The spring force changes with the amount of stretch. If you see a problem where the spring is changing length, that's a pretty good clue. You might need to use this attack, at least for right now. In Physics 162, we can handle it another way. All right. If the spring is not changing length, if a spring is a fixed length, Kx is a constant and you could do an FBD. Okay. So just watch out for that. Problem 8.11, which is one we kind of skipped over, we'll go over that in detail. So this is a subtle thing. You better make sure you do 8.11, okay? Now, and then for pendulums, it's not always this way. It's just almost always this way, where the angle to the vertical is given, and you get this result. That's the key tricks that we have seen for solving these problems. All right, let's take a short break, take about 5 minutes, and then we'll come back and we'll do a couple more things, introduce the last part of chapter 8. All right, and then we'll continue with chapter 8 next week. But yeah, come back in 5 minutes, all right? Unless anybody's got questions about this summary. All right, let's say 6:17, all right, on this clock anyways. So it takes 5 minutes and then we'll be back. All right. All right. Man, I wish Alan was still here. Sorry I got so snippy with him. I'd let him know that. It's just very difficult when you're trying to work with a large group of people, and then I don't like addressing a one student question in front of a group of large people because they're all waiting. I don't mind addressing the question. It's hard to do it when you got a lecture. That's the issue there. I don't know. All right. Well, so I'll talk to him later. I'm sure I'll see him later. All right. So now I'm going to kind of foreshadow an interesting thing with a weird problem. It may seem silly at first, but I just want to do it. So let me, we're going to pick up at the next page, I think, in the workbook. Where is it? Here. All right. So now we've already been using this, but now I want to give you kind of the general definition just to kind of see. So you can use a force. And if you recall, this is work. The integral of force.ds. This was the definition we used to start this chapter to get on this path of potential energy. So if I rearrange this a little bit, there we go, rearrange it a little bit. And then just like in the, whichever chapter that was, I forget, chapter 2, we do this relationship where we say, okay, let U final be U of X. So this is the potential energy as a function of position. Now here, there's going to be some initial value, just like before, and then minus the work done, right? Okay, so as a worked example, let's look at this one. Suppose you have a horizontal spring, okay? So the force is Kx in the negative I hat. All right, so if I want to use this F sub X, that gets rid of the I hat, but it keeps the minus sign, right? So it's negative in the I hat. All right, so far so good. Yeah, that's annoying, but whatever. All right, so when we go through here, we do this. Notice this minus sign cancels this minus sign, and we get this 1/2 kx squared. And then I think most of you will agree, if the spring is unstretched, it should have no energy. Well, the spring is unstretched when x is equal to 0, because by definition, x was the amount of stretch. So for us, it seems reasonable in this case to set u equal to 0 at the origin when the spring is unstretched. And so that is how we get this spring potential energy. We've been using it. That is the derivation of it. We're going to use this again in chapter 13 and in electricity in physics 163. So just kind of keep this in your bag of tricks and let me show you more on that. All right. Now, in this case, this is the part that's going to seem a little silly at first. Okay. I'm going to point out some units here. This is 0.02 meters and it's negative. All right. Now, the reason I'm doing that is because the spring constant K was given in newtons per meter. So when I plug this in, the 100's going to shift it right back, but there's a minus sign in here, right? And so we're going to get minus Kx. For the first one, I think if I do all the math right, it should be positive 2. Similarly, this is going to be positive 1. When there's no stretch, there's no force, negative 1 and negative 2. So I'm just going to plot that out on here. Should look like that. Sorry if it's not perfect. Okay, that is the force. Great. What about U, the energy? Well, the equation for that one is 1/2 kx squared. Okay, so when I plug in those numbers, K was 100, 1/2, that's 50 times x squared, but we've got to use meters. So it's 50x squared. In this case, that's going to be times 4. And then notice I wrote it in millijoules. So we get 20 millijoules, 5, 0, 5, 20. So the energy is always positive. It looks like, I'm just going to freehand this here. Let me put some dots here, 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 here. It's not very great, but it's close enough. All right. So in this case, this is the part I want you to learn from right here. Okay. We know by definition that u of x, and actually delta u, I should just, let me say delta u just to save my, let me just say it this way. Delta u is equal to minus the integral of force dx. What is the opposite of this integral? What is the opposite of that mathematically?
Derivative?
Derivative. So we can say f sub x is equal to minus the derivative of u of x. That happens to also be true. What does the derivative mean when we have a plot?
Slope.
Exactly. And that's why I'm bringing this silly stuff up, so I could show you these relationships. So give me just a second to finish writing this. It turns out the force is equal to the opposite of the slope of the u-plot. What? So in this case, let's start right here. What's the slope at the origin of the u-plot?
0.
There's zero force. So far, so good. And then how about here? Right here, what do we have? In this case, the slope is positive, and notice the force is negative. Over here, the slope gets even larger, and you see the force gets even larger and more negative. Similarly here, we have a negative slope, we get a positive force. A large negative slope, we get a large positive force. So this result we see matches up to what we expect on this plot. That is going to be useful. In practice, in a number of disciplines, it turns out it's easier to get this plot and then use the plot to figure out this force. And we actually use the energy equation to figure out force using this slope trick or this derivative trick. That is a big deal. Questions on that? All right. So now, if 8.22 is a question you can do, let me just go back here. This is kind of a summary of that. And so I'm going to talk about this in just a second. I scrolled past a couple of problems, but so page 22 is going to be the summary. So that said, I don't want to forget to say things about these two problems I scrolled past, so I'm going to mention a couple of things. This is only true for conservative forces. Conservative forces mean the work done is this right here. So work done on a closed path is 0. And so there's no work by any any path going from point A back to the same point. And the work is independent of path, the same amount of work no matter which path you travel on. Now, if you're curious here, the whole point of this problem is just to show you that the work done by a zombie on a string is not conservative, right? The point is there's a plus sign in one direction, there's a negative sign in the other. So when you're doing a zombie string problem, we don't expect the zombie tension to be a conservative force. So this would not be valid for that. We've already seen it's not valid for friction. So we don't expect friction or zombie tension to have these rules apply. So we can't do the slope and crap for those. Here's another example of a conservative force. This is called an anharmonic oscillator. So at some point, particles don't act like they're connected by springs anymore. So what do? This is the spring term. You add on an extra term, and you just keep adding on terms. Kind of like a Taylor series, right? You can just keep adding on extra terms until the force modeled actually matches what you see. So that's cool. You could do that at home. And now I want to get into this one. All right. So, and actually here, let me see if I've got this here. Whoops. Let me see. Where was it? It was, oh, I guess I need a new window. Sorry about that. Boy, that's very meta. Watching, yeah, strange. Hold on. So let me do Fet Leonard Jones. There we go. Sorry about the delay here. All right. So I'm going to start by talking about this. This is actually the same thing that we were just talking about. Okay, we've got, let me get an annotation here. This is X. This is U. So this is a plot of U versus X. U versus X, all right? Now, in this case, I'm going to go to the custom just to make this more visible. All right, and let's just make this crazy. No, this one. All right, do I want to spend too much on that? Probably not. All right, let me make this a little bit less intense. And so what I'm going to do now is I could take this atom and I can move it and let go of it at any point on here. All right, so for example, let's say I start right here and let go of it. We see this is a model, and somehow this plot of U versus X relates to the motion. So to understand this, I'm going to slow it down. And remember, we're looking at a plot of U versus X. So as I step forwards here, what should be the force on this atom at this point?
0.
Yeah, so let's look at it. Notice there's not much force there. As I keep stepping the simulation forwards, what should the force be? So keep in mind, a second later in the simulation, we're probably going to be sitting right over here. Do you think the force will be large or small, and will it be positive or negative?
Be large positive.
Huge. Nice. And so now, as we go back down and we get to the other side, what should happen to the force as I go up on the other side? Negative, but not as large. And so notice the atom is actually able to go farther to the right than it is to the left. Do you see that? It's because the slope is more gentle on the right side. As a result, you get this basically implies there's less force on the right, so it takes longer for it to turn around, so it travels farther. There's a lot of information hidden in here, right? It's crazy how much information. Now, here's the crazy thing. We can actually pretend that that plot here, that red line in the picture, this curve that I'm pointing at right here, this curve right there, that curve you could think of as being a frictionless track, like a roller coaster. All right. And this is a marble on that track, and it's going to roll around. And the direction the marble rolls towards the left side of the graph or the right side of the graph helps you understand the force. So think about it. Here, the marble would naturally want to roll down the hill. That would cause it to go to the left. The force is to the left. When the marble's over here, it would want to go to the right, and it would want to go there quickly. And that makes sense. So here, the force is to the right. All right, so let's clear that out and try to think about this as a marble on a track. Which way would the marble roll? Where would it be fastest? Where would the force be largest? And all of these things seem to make sense. And if you're curious and you're a chemist, you can see that there's actually a couple of different forces at work here. So there's an attractive force, the van der Waals force, and then there's a repulsive force. Basically, the electrons don't want to be on top of each other, right? Two opposite charges want to repel each other. And so that's what's happening here. And so this is a complicated problem with multiple forces, But by using this energy plot, we can simplify it to a single force, the net force, associated with this conservation of energy, because these are both conservative forces. So in practice, we could use chemistry to figure out this curve and then use our knowledge of potential energy and force and slope to understand forces and animate the motion. And you can see how this changes for different atoms. And so you could actually relate this to, well, look at that one, oxygen, oxygen. Got this. Okay. And I don't know. I'm going to pause for a second and see if there's any questions here. So, yeah. All right. So let's go to the book. All right. So let me see. If you're curious, we'll start up here next time, 8.24. But we probably don't have time to do this one today. So we'll start up there next time. But this is the same problem, and we could talk about it later. That said, there's a couple of things in this bullet point I need to explain. All right. So remember these things. Number one, the minus sign. Force is opposite of the slope. Underline the word opposite. From that, when slope is 0 of the U-plot, the force is 0. So sometimes you'll see a question say, what are the equilibrium positions? Now, here we see something interesting. Equilibrium points are classified as stable, unstable, or neutral, depending on this concavity. So let me show you this on the plot below. Sorry for those horrible grid lines. Now, in this case, this is a stable equilibrium right here, 0 slope. Unstable, I'll explain why. Stable, and this is called neutral equilibrium. The key is, think about what happens if you provide a small displacement from equilibrium. If I put a marble a small distance to the left, it's going to oscillate back and forth between those 2 red points shown. That's what it means to be stable. If you're pushed slightly away from the stable equilibrium point, there's a force that causes you to come back to that. We call that a restoring force. So there's a restoring force in a stable equilibrium. You tend to oscillate about that. Now, what about over here? If I push you just slightly to the right, not only is there a force away from that equilibrium, that force continually gets larger. So this is extremely unstable. As soon as you're pushed even the slightest bit away, you're more and more likely to move more and more rapidly away from that equilibrium. That is unstable. Okay, so stable and unstable are usually pretty reasonable for people. Neutral is a little bit odd. So I'm going to just exaggerate this even more. So in this case, assume that line is perfectly flat. Okay. And now, again, it's all about what happens if you displace it slightly. Let's say this thing is sitting here and I bring it over here. Okay, I applied a push and now it's moving. Is it going to speed up or slow down after I give it the push? So the push has been given, it's moving with some speed v. How is that speed going to change? Think of it like a bead on a roller coaster. If you move a little bit to the left on here, the height hasn't changed. You haven't converted any gravitational to kinetic, same speed. So neutral is one where if you displace it, it will move away, but it doesn't accelerate away. So if I could talk about this in terms of accelerations, here the acceleration is 0 for a small displacement. Here, the acceleration is away. You accelerate away. And here, you accelerate back to equilibrium. So if you can think of them that way, it kind of makes sense why neutral is included. I'm going to pause there and see if that makes sense on the equilibrium. Any questions on that? So that is the classifications of equilibrium. All right. Every once in a while, a test question or quiz question might be identify the stable or unstable equilibrium points or whatever, or characterize the equilibrium points. So that's why I'm mentioning that. Okay, now you keep hearing me talk about this. Think about how a marble would roll to get a feeling for the direction and size of the force. Okay. So if we put it at x equals -5, let's see, here's x equals -5. So if I put it on the track right there, we would expect it to speed up and go to the right. So it would travel to the right. It would go down here, and then it would start slowing down, but it'd still be moving. It has enough potential. It has enough kinetic energy to make it over that hill, speed back up, and then we'd expect it to go here, and then it would keep traveling to the right, and it would go away forever. Now, to be clear, this force is describing something moving left-right, purely left-right. Okay, it is not actually moving up and down like a roller coaster. However, this analogy tells us the marble, if you had a marble that starts right there, it'll end up over here to the right. Again, just like this one. Whoops. When we run this thing, whoops, oh, I forgot to pull it, right? Let's run this normal. The idea here is the atom is moving left-right, but the marble is moving around like it's on a roller coaster. So again, these plots, you don't want to think about them as being actually a marble on a roller coaster, but that can give you a feeling about how things should work. So notice this is a stable equilibrium. Tell me, if I originally compress them together and let go of it, what's it going to do?
Try to move apart.
How far will it go before it reverses direction?
I don't think it won't reverse direction. It'll just keep going because
Exactly. It doesn't, the potential well doesn't rise up to the same height on the other side. So this would be like the skateboarder on the track is never going to come back because right? Once they get over here, there's no force to the left on them. Nice. Okay, trick question. Okay, so going back to here, some units, information on units. Unfortunately, we always have to deal with them. Nanometers, 10 to the 9th meters. Milli EV. E is the magnitude of charge on an electron. EV is called an electron volt. Basically, it's a very tiny amount of joules. So an EV is 10 to the minus 19th joules, 1.602 times 10 to the minus 19th. So a milli EV is about 10 to the minus 22 joules. So for atomic problems, EVs is a much better value, right? Because you could imagine atoms have a very tiny amount of energy. All right. So why do we care about this? Why do we care? In many real life situations, it's much easier to create models for energy as opposed to forces. Once the energy is modeled, we could figure out the forces with derivatives. You could use it in quantum chemistry, quantum mechanics, electrical engineering. Electrical engineers, you're going to learn about things called band diagrams, whatever.